Okay, so I think Elise, you're going to be the only one listening to this, Elise. Sorry, I forgot to start recording until now. You're going to have to read these definitions on your own. Okay, yeah. Okay, so let f be a function with 5 derivatives on the interval 2 to 2.7. So we're talking about a pretty small interval, right? And that would make sense because when you draw those, the nth degree polynomials, remember you have to add a whole bunch of terms for them to be on a large interval. Okay, so we're working on this small interval here. And that a 4th degree Taylor, 2 to 2.7. Assume that, what does this represent? Those symbols? Absolute value of the 5th derivative is less than or equal to 0.2. Okay, you've just been given that piece of the Lagrange, right? Okay. For all x in the interval 2 to 2.7, and that a 4th degree Taylor polynomial for f at c equals 2 is used to estimate f of 2.7. Okay, so what you've just been told is I have made a 4th degree Taylor approximation or polynomial approximation, right? And that would be it. If I were making the 4th degree Taylor polynomial approximation, this is what I'm essentially doing, right? I'm doing the 4th degree polynomial at 2.7, and whatever is left over would represent f of 2.7. F of 2.7 would equal that Taylor polynomial approximation plus whatever remainder is left. Do you agree with that, big picture wise? Yes, Michael?
Like, what is the remainder part?
That's what we're getting, that's this right up here. So, right, if I only went to 4 degrees, whatever is left after the 4 degrees is what I'm referring to as my remainder. Okay, so that represents the 4th degree polynomial. This represents the remainder associated with the 4th degree Taylor polynomial. That's what that 4 represents. Okay, so the question asks you how accurate is your approximation. Okay, well, I just learned up here that the absolute value of that remainder or error must be less than or equal to the max of the absolute value of the 5th derivative of x times the absolute value of x minus c. What is x in this problem? 2.7.
Wait, what, do we need the Z?
I'm not there yet. Okay. Well, here, you can change that. You can make that a z. Sorry, make that a z. So we stick to our formula. Okay. Times 2.7 minus 2 to the 5th power all over 5 factorial. Okay, not enough of you are answering. This is what we're using. The remainder associated with my 4th degree Taylor polynomial must be less than the max the 5th derivative at z can be times x minus c to the n plus 1 over n plus 1 factorial. Well, if I was dealing with the remainder of the 4th, then n plus 1 is the 5th. And remember, x is the value that you're interested in. C is the center. Yes?
So is C just representative of the x value where the...
It's the x value between, yes, it's the x value between 2 and 2.7 in this problem, where the derivative would be a max. that's gonna be the maximum I could be off, right? Is where the derivative is its greatest. Like if you're thinking about it in terms of a picture, like if this is the actual function, it's like where that, the difference in the steepness at those points is kind of what we're talking about. Okay? So, so in this particular problem, they gave me the max the next derivative could be, didn't they?
Yes.
And it is what? 0.2 times, and then well, this is going to be 0.7 to the fifth over 5 factorial, right?
And should that be the fourth, remainder of x, or is that c also?
No, this is x.
That is x.
That is an x. Just like it was up here. Okay, and you should have a calculator, and that comes to, and it did say to go to 5 decimal places, just so you know.
So, we 0.00028.
Okay, so again, that is the maximum your fourth degree Taylor polynomial could be off
Either way.
if you're working in the interval 2 to 2.7.
That's either direction, right?
Hmm?
It could be off.
Correct, it could be off either direction. Okay?
It could be off either direction from.
From from your Taylor, well, look at part B.
Okay.
Suppose that P of, the fourth degree polynomial at 2.7 is 1.763. Use your answer in A to figure out where f of 2.7 must lie. Well, f of 2.7 would have to lie in between where?
1.763 plus or minus.
Yes, 1.763 minus that, or 1.763 plus that. Does that make sense to you, that that's where the actual value has to lie between your approximation that you made using the fourth degree polynomial plus or minus the remainder associated with it? And like, if you really stop to think about the fact that you're able to compute that, it's kind of a cool thing. I mean, if you're in this for the beauty of mathematics, right?
So what does that represent again?
This is where this was your you used a fourth degree Taylor polynomial to estimate f of 2.7. We don't know what the function was in this particular case. Okay, but you used a fourth degree Taylor polynomial to find its value. And what we're saying is the actual value would have to lie between those two numbers based on the error that you calculated. C says, could 2.7 equal 1.7621? Why not? Why not?
Yes. No.
No.
Right.
It's
It
not
lays outside of
in
that.
Right. No, not in interval. What about 1.7631? Yes. Because it's in the interval. Yes, Michael?
So like, I keep wanting to look at it as a graph, and is this talking about like the y, like value?
Yes, it is the y values. So, these are the y values when x is 2.7. Okay? So when x is 2.7, the y values have to lie, the y value has to lie between those two numbers. Okay? It's kind of like, if you go back to the tangent lines approximations that we learned way early on, f of 2.7 has to lie, if you didn't know it, but you knew these, like, you can approximate the y values on that curve using this tangent line. And if you could approximate those values, then you'd know the real one had to lie in between there. Does that help? Let's go to one where we actually have to calculate it, Michael, and that might help you a little bit more. So turn the page. What?
Yeah.
We do? Only 2 minutes left? Okay. I'm going to talk as long as I can. Find the fifth degree Taylor polynomial for f of x equals sine of x, and use your polynomial to approximate sine of 1.5 and use Taylor's theorem to find the maximum error for your approximation. Give 3 decimal places. Okay? We can all write the fifth degree Taylor polynomial for sine of x, right? What is it?
X minus
X minus
X
X
cubed.
cubed over 3 factorial plus x to the 5th over 5.
right? There it is. And I'm supposed to use that polynomial to approximate sine of 1.45. Right? And you get 0.995. It says use your answer in part A to find the interval on which sine of 1.5 must really lie. So what are you going to have to calculate first? The error. So the remainder associated with the fifth degree Taylor polynomial that I just used has to be less than or equal to the max, the absolute value of the sixth derivative of sine of x times 1.45 to the sixth. It would be minus 0, right? Because it's centered at 0. All over 6 factorial. And then let me say this to you really quickly. What's the max any trig derivative can be? Sine or cosine? 1, because it's the max value it can have, right? So it would just be, that's 1, this all comes out to be 0.0129. Okay, so that means that the actual value would have to be somewhere between this plus 0.0129 and that minus 0.1029.
So the absolute value of the derivative changes to 1, and then you just have the absolute value.
Yes.
Okay.
Yes, ma'am. Okay, I'll put the remainder of these examples up or send them to you, and you'll just have to deal with more text from me, sorry, so that you can get them. What I would like for you to do for the homework, there are 3 problems on the back along with the answers, and I would like for you to give those a whirl, okay? I am going to leave a worksheet with Mr. Bailey for tomorrow that you guys can do in a group, but you will have to turn it in, okay? It's going to count as a grade, so it'll be like a quiz, but not really, okay?
That's great.